Corporation, who's going to be talking to us about Digital Engineering Integration Committee at the AIAA. I would like to point out that this committee recently got an award from AIAA on the wonderful work that they have done. So that was my motivation to invite him over for our seminar talk. I'll just quickly introduce Matt French. Matt French is a staff engineer, systems architect with Northrop Grumman Corporation. He is part of the Enterprise Open Architecture team, where he provides systems engineering and architecting leadership for future aerospace systems mission capabilities. He has an industry experience in systems and electrical engineering, and he's been a retired U.S. Army officer with 23 plus years of service. And a really welcome thing is that Mr. Matt French, he received his bachelor's degree in electrical engineering from George Mason University. And he got his master's in systems engineering from George Washington, and then another master's in system architecting from USC. He's an INCOSE certified systems engineer, and he's also an associate fellow with the AIAA, that's American Institute of Aeronautics and Astronautics. So with that, welcome, Matt, and thank you for taking out time from your busy schedule. And I'll hold the floor. I'll put the floor over to you.
Great. Hey, thanks, Ali. Yeah, this is a accumulation of work that's been done within AIAA for digital engineering. This is a relatively new committee. So within this, I'll go through a couple of different things that might help just set the stage to make sure we are all understanding what is meant by digital and why are we doing this whole digital engineering transformation. We'll go into a little bit about the Digital Engineering Integration Committee. You'll see it references DEIC throughout the presentation. We'll go into what that is. We'll talk a little bit about teamwork and why this is a challenging problem to work with. Then we'll get into some digital twin work that we've done and some other artifacts and some next steps for Digital Engineering Integration Committee. As Dr. Roz mentioned, I am a George Mason alum, so I appreciate the opportunity to talk to everybody. I have fond memories of doing my undergraduate degree there at George Mason. So let's start off on kind of why are we doing this? Start out with the why. As systems engineers, I say we're the guardian of the why. You got to understand the purpose behind any effort. Digital engineering is a big endeavor. You'll see how big a scope it is, and you can get lost in the forest here and forget why you're doing this to begin with. And connecting it from the top level, why are you doing this, down through all of the different efforts, it's systems engineers that do that. So we'll keep this in mind. Why are we doing this? So there are several different reasons that digital has a lot of potential benefit. The first one on the left-hand side is because of, this is from an INCOSE handbook, where we know that costs in late life cycle go up. And so if you had to make a change in late life cycle defects, it's going to cost you an enormous amount of money to make those changes. So the whole purpose of this digital transformation is to move the right side of the curve to the left side and find those defects in electrons in modeling rather than in atoms in something physical where it's very expensive to fix. So the first one is move. See if you can see in my mouse, we're going to move these late life cycle defects where stuff is in physical phase to the left. The next one is over here. This is out of a DARPA. We call it the hockey stick chart because of this hockey stick thing here, where it's showing that, especially with defense aerospace costs, they're on an unsustainable chart trajectory. And so this is showing that other people have started to make the turn. This is automotive down here. This is commercial aircraft here, flatten the curve a bit. But military, is on an unsustainable trajectory. So there has to be something done. The last one over here is that DoD is mandating it. It's in their strategies and it's in their policies, and they're primarily doing it for speed. If you had to pick one thing that they want to do, it's get solutions out to the warfighters faster. And so they want it for speed. And when you move these last couple of phases earlier in the life cycle, you can achieve speed because you're not fixing things out here that take forever to fix and are very expensive. So we're talking about speed, but you have to have a whole life cycle perspective. I'll bring that up in a couple of slides. Dr. Roper from the Air Force, he's been championing digital engineering very publicly. There's a lot of great papers that he's put together that help show what does he mean by digital engineering within the Air Force. And, you know, here's their speed. They want a greater than 50% step change in from concept to production. You know, how are you going to do that? You got to change the way that you do things. You can't just keep doing it the way you've been doing it. And these are the how he plans on doing it through digital engineering. You'll see a little bit about that in this presentation. Agile software development. I would argue that it's really Agile systems engineering development that enables Agile software, but I'll give a little bit of talk on that. And then they're looking at modular open systems architecture, and that's what I do at Northrop Grumman. So the important part is this last bullet where operation and service constitute 80% of the total costs. So a lot of the work that's been done upfront in design work, it's important. It absolutely is important. It's the fun part. This is where the money is spent out here and where things are out in the field and how much the cost gets associated with it. So that's a really important driver for thinking of a total life cycle. This is probably the biggest why of what needs to be done here. When you get through all of the total life cycle view, all of the different elements that make it the cloud, the digital thread, digital analytics, model-based X, and that could be model-based systems engineering, model-based enterprise, model-based safety analysis, model-based anything, and all of the what-if simulations, really it all comes down to making better decisions. And so if you're not impacting the customer, allowing them to make better decisions through all of this digital information, you've kind of missed the point. So this is kind of an important slide, and people lose sight of this important distinction, that you're really helping the customer make value decisions. So what do I mean by digital engineering? I've got a couple of cartoons that kind of showcase this. So if I look at how things are today and the siloed process across a life cycle, everything gets kind of thrown over the wall from design, where you get printouts, CAD models, you get thrown over to manufacturing, where you got other individual islands that fabricate a product. And you got MRB, which is concessions, which is a huge portion of, there was an error in fabrication. Is it okay? Or do we have to scrap that material completely? Can it achieve the life that we expected? Or can we use it? Then you move into after it's fabricated, you throw it over the wall to another group of people who assemble it, another group of people who qualify it. This is a military type thing. So military has qualification, commercial has certification. So do you do military qualification, or are you also going for civilian certification through FAA in the US or EASA in Europe? And so there's a big effort here. And usually when things are found here that are bad, you go back to here and you have to start back over. So there's a lot of back and forth in here. Then you can sell and deliver it. Finally, you're finally starting to make money, and then you're into over here where you're starting to use it out in the field. This is the way it's traditionally been done, and it's very siloed, and it's one wall over the another, going all the way down the life cycle. It is extremely expensive and it takes a long time, decades, to get something through this process. So what is digital engineering? It's meant to go to where you're starting to build up they're now calling it a tech stack across the bottom here. That's all based on value, from your customer's value. What do they need? And you're enabling decisions off that. You're starting to layer in more information. And then you're layering in the information that's flowing between all of these different areas. No longer are you looking at design as an island. Now you're looking at how it affects all these other elements. In systems engineering, this is not new. We've talked about a collaborative life cycle view, and this is what we're talking about. So systems engineers are key to enabling this life cycle view. And finally, you get the data across it all that enables these things to be connected. So when you get these things connected across all of these different silos, that's AKA a digital thread, that's the information flowing. So that's one way of looking at it. Another cartoon that I've put together that helps illustrate what do I mean by digital engineering to people, because it's kind of a big concept. I've put together a chart here that kind of shows from a top level perspective. You have a digital system here that we're looking at. You have a security that has to be in place to enable it from a cybersecurity perspective. And you're overlapping it with a business opportunity. If there is no business opportunity, this digital system and the security are not needed. So you got to have a business opportunity you're going after. And so when you have the business opportunity and you have security in place, this digital system only then can be enabled. And so what I'm going to do on the next slide is go a little bit more into depth about this digital system. Just keep in mind at this top level that it's overlapping a business opportunity and a security aspect. Inside the digital system, we break it into four large buckets. We have a digital product. This is the digital system. This is not the physical system yet. This is a digital product, and you have a digital environment. And I'll talk a little bit about that one because a lot of people forget about this side of this equation. Digital infrastructure, that's enabling these things to happen. And you have lifecycle analytics and methods, either Bayesian belief networks, some kind of CFD models that allows these lifecycle analytics and methods to be enabled on the digital product and the digital environment. Where these four big bubbles overlap is where you start to see what people tend to think of about a digital thread, a digital twin, stuff like that. And so I've lumped these into areas across here where we're saying, you got to have a sensor fusion to enable digital product connected to some kind of high performance computing system. You got data centers. You're going to have some way to enable this digital product to connect to an infrastructure to once you get a physical product out there to enable it. Same way, the digital environment, all the digital products experience different elements across the life cycle. So you have to start modeling the environment that these things go into. That's how come when you enter the manufacturing floor, you'll see this coming up on a slide, you start modeling not only the manufacturing flow, the manufacturing process, the manufacturing machines, but you're starting to model more than just the digital product. You have to start, because these things have a real impact on the product. Such an impact that you'll have a digital product that's modified because the digital environment modified it. And the important part that a lot of people want to get out of all of these three elements comes in this bottom piece here, lifecycle analytics and methods, where you want to get into predictions. How can you predict in the future how well you or bad your new system is going to behave? Is it going to have intended behaviors and operate as you thought it would in a new environment, or is it going to operate differently than you thought? You want to try and predict that rather than experience it in real life. So you get these predictions here, both geometric and functional and environmental predictions through a lot of these lifecycle analytics. And the behavior goes down to the material level that you start getting into the behavior of this. So this is another viewpoint of how to view, viewpoint for a view, you like that, but look at digital engineering. So it's much bigger than just the digital product. When you look at it across the life cycle, what we're talking about is as designed, and this is new product introduction, NPI, you go through certification and you get the as validated product, and EIS is entry into service. So how do you connect these two big portions of the life cycle? Inside an organization, usually this is a large portion of your organization, a very large portion. Same as this. This is usually a large portion of your organization in a separate site, separate group of people, even separate countries that this is found in. So how does this as designed intent get put over here to the as built product? And then finally, over here in service, you have a whole different group of people and customer that see it and experience it. How do you connect all these different elements? And CPI is continuous product integration improvement, actually. So you're looking at how do I bring all of the defects that I'm experiencing here back to design and redo it? Or after I experience it in manufacturing, the defects that I found, I go back to design and redo it. I want to minimize those loops. That's the whole purpose of getting changes in electrons here versus in atoms out here when things are real. The problem with this life cycle is people, different groups of people, different training make up these three big bubbles of design, make, and use. And so in design, your foundation is on beliefs and intent. You're not actually using it in the field. A lot of the stuff that you're doing is on intended, I'm designing it for whatever. Whereas in make and test, the reality is on uncertainty and in variability. Now I'm trying to reach a Six Sigma kind of tolerance level, and you get tolerance stacks where I can have a 1 sigma tolerance on one area, but now I've got another tolerance on another component, and together I'm at a spec. So now you end up with a different take on the product in a different area here. And finally, in certification and use out here, it's confidence. Can I use the product to do my mission? And if there's any lack of confidence because of lifing issues, because of costs going up, because of material not being available, supply chain not being available for building out pieces of what makes it, I'm now starting to erode my confidence of being able to do my mission. So there's three very big and different perspectives that have to be accounted for when you go across this life cycle. And you've got to look at it from a life cycle view. So with that kind of understanding of what is digital, why we're doing it, I'll get a little bit into the Digital Engineering Integration Committee and how we're tackling those issues. So just a real quick one chart summary of what the Digital Engineering Integration Committee consists of. We have 5 committees. I'll talk about that on another slide, but we have a membership of about 75 actual members, 107 if you include friends that we make aware of what we're doing. It's actually probably higher than 107. And you can see the breakdown between industry, government, and academia, their percentages. Some of the things that we've been doing, we get a lot of work in the different AIAA forums and other forums that are like-minded in topic. So digital thread panels, digital twin summits. We hold a lot of technical interchange meetings with government, AFRL, Air Force people. So, and then we've started to do some short courses within AIAA of what is digital engineering? How do I approach this? And it's a bit different than just traditional approach to products. We're starting some publications, the digital twin position paper that we've just launched. I'll talk a little bit about that in coming up slides, that we've done from a joint with AIAA and AIA. And I'll talk about why that's important coming up. And then we have liaison activities with a lot of different professional societies. And that brings up an interesting situation when you're looking at different societies and how they approach this differently. Inside the DEIC, we have 5 subcommittees, 4 listed here. One's looking at the ecosystem, the digital ecosystem that deals primarily with standards, policies, and DoD guidance, or even commercial guidance we receive from a lot of organizations. What's important about this is the value proposition. If you look at it from a DoD perspective, the value proposition is speed. I want to get my product to the end user faster and continue to get it there faster. If I look at the value proposition from a commercial perspective, it's money. I got to make money for my shareholders. I also value national security, greatly value it. So there are shared values there, but there is some value that business sees differently than DoD. And so there's different values that start to shape how you approach these things differently that need to be accounted for. We have the digital system model that takes the lifecycle view across all model-based MBX, model-based everything across the entire system. And how do they start to integrate together? How do they play well with each other? There's a lot of modeling activity that goes on. And if you rely on the tool manufacturers to make the tools play well with each other, you're never going to get there. That has been a fraught activity from many different organizations, spending hundreds of millions of dollars to keep tools working well with each other. And there are hundreds of tools. So you have to approach it differently. And there are a lot of thoughts on that. Finally, we have the digital thread that allows the end-to-end connection of information, really. Don't think about it as tools. Think about it as information that's flowing from different groups of people and different tools. And then the one that's getting a lot of publicity and a lot of emphasis is digital twin. And we'll talk about that one a little bit more, so I won't get there. I said there was 5 subcommittees, and that's because the 5th one is the steering committee that goes across, I thought I had another slide, that goes across all 4 of these subcommittees and helps keep things organized and consistent. So real quick, the digital ecosystem is subcommittee is the one that's responsible for understanding how all of these different subcommittee elements, such as digital thread, digital twin, digital system model, heck, even certification by analysis, which is a growing body that we'll probably have another subcommittee on. How do they work well together? And so you get into a lot of standards. You get a lot into open architectures. You get into a lot of these different elements and how you do things, and they are connected. So this one goes outside AIAA and starts connecting other committees together. We're working a lot with AIA, COSI, and other bodies that are out there. I'll show you a little bit of the sampling of those. But they are responsible for how do we set up the environment by which we can go work on digital engineering. The digital system model is probably the least understood one of them all, because it is, where does the, for instance, one of the questions we're wrestling with right now is, where does a digital system model end and a digital twin start? This is the precursor for it. Where is it? Where's that transition occur? That's you get 4 people, you get 5 opinions on it. Everybody, and they have strong opinions. So there's a lot of working within the organizations to try and figure out what is this supposed to do? How you work with a digital system model, even if we had this together, all this model together, which a lot of organizations do in their single organization, but when you start connecting it across a supply chain, things start to break down. So if let's assume you had them all together, what does that give you? What's the value behind it? And that's where you wanted to have this authoritative source of truth. Truth is a word that get a lot of people upset. They rather call it authoritative source of knowledge, but truth is the one that got put in there. And how do you update it, and what does this become? This is an area that is a lot of investigation going on. Digital thread overview is really the information. This is the information that's flowing from the design world out through the end user. And there have been a lot of great models put together on this. This one on the left is put together by General Electric, mainly for the wording around a very familiar type of diagram, but it shows that it's never ending and it's continually updated. But all of these different life cycle phases should not be equal in cost or how much they are active. If you got a lot in updating, you're going to have a lot of problems in maintenance. You want to minimize this as much as possible. So there's an emphasis to put a lot more up front, but it's never ending basically going on here. So there's a thread between all these different elements. Another one is this Boeing Diamond. If you haven't heard of it, I would encourage you just to Google Boeing Diamond, and you'll see this type of diagram and a lot more information on it. This is I'm just scratching the surface on a lot of these topics because there's so much here. And they've taken the traditional systems engineering V down on this bottom one, where you go from design to physical, and created this inverted V on top, and showing the relationship between every one of these vertical elements over here, then here, and here. They line up across the whole life cycle here, if you're looking at from a modeling to design perspective. And then you're looking at it from a horizontal viewpoint, from a model to virtual. You line up the dots across this way to understand what it means to go from model-based systems engineering out to virtual certification. For instance, there's a line across there. And what enables this top V and the bottom V to get connected is the digital thread. And there's a lot more in this. And Boeing has done a great job looking at how to represent it. Same with GE on this. Is it complete? No, it's not 100% correct, but it does a really nice job explaining the situation and having people comprehend it and get a mental picture. Part of the problem is you get different mental pictures put together by different people, and they're talking in different circles. So this at least puts people on the map of finding out where they need, what we're talking about, and what they can disagree with or agree with. There's large agreement with this model, though. So I'd recommend going to Google Boeing Diamond. Finally, the digital twin subcommittee. This is where we have a model that is a direct representation of a physical asset. And with that model, you are because it's connected to that physical asset. Each and every physical asset has its own model associated with it. So if you have a product line of 10,000 products, each product has its own digital twin. And that way you can look at each one of those assets and understand what can happen in the future. What if I had a tolerance of, I'm barely meeting spec on one part, but I'm over good on the other parts. How can I affect my life? Well, that piece, that one physical asset might be different than another one that came off the same assembly line, because the subtractive manufacturing drill bits do wear. And when one product has a tolerance of X, the next product coming off the exact same assembly line will have a different tolerance, because the manufacturing machines, they have wear and they're going to wear out. So you end up with a digital twin of the manufacturing machine to predict its life, to impact this physical asset life. So it gets big. Just keep in mind, digital twin is by asset. Okay. I'm going to keep moving along quickly here. Get into the teamwork, a couple of cartoons here just to have fun with this. This is just recognizing that depending on who you talk to, you're going to have different mental pictures of what it is you're envisioning is the end result. So whose job is it to connect all these differences of opinions across what the end product looks like? That's the systems engineer. And so when, this is one way of looking at it, of what the end product looks like when you're looking at it from a marketing perspective, from a customer perspective, from a life, services perspective. There's another way to look at it, and it's also the job of the systems engineer to deconflict all these different mental models. Within engineering, we have different ways that we would envision it, because that's your areas of expertise. So in this, excuse me, in this example, each engineering discipline is going to highlight their skills. That's their natural ability, is inside each of these different areas. So wing groups can have large wings. A power plant group is going to have a large engine. You're going to have, a stress group that's going to be made up of a lot of I-beams, and it will probably never fly, but it won't come apart. You have different groups highlighting their skill sets. Who is job, and it's the systems engineer's job to deconflict these and get back to the why. Why are we doing this? So this team work of understanding the differences comes about, and it's important to keep in mind. And this is due to the depth and breadth that I'm going to talk about with digital engineering. When we talk about the depth, we're talking about from a systems perspective, all the way from a system, all the way down this whole chain here, down to the material level, which is involving hundreds and hundreds of different supply chain companies. So you end up with a very deep reservoir here of people and groups and disciplines working together. And that's just from a physical sense of systems of systems all the way down to material level. You also end up with it from a mission sense of these operational models or ConOps of what we want this thing to achieve through the system models and the component level models. So it's a very deep lake here that we're trying to cross. So there's a lot of differences of opinions across this entire spectrum. And you get in with digital engineering and moving everything from the right-hand side of the V to the left-hand side of the V, you're trying to do everything virtually. So you got a virtual design environment, virtual life cycle environment. So all of this is now virtual before you physically build or test anything. Virtual verification. So I'm going to test it. I'm going to demonstrate it. There's a whole new Air Force E-Series aircraft and along with this virtual verification environment. So a lot of these things are now all virtual across this whole spectrum. And that's a depth-wise, and breadth-wise, you end up with connecting, like I mentioned earlier, design to make to use, which is the whole life cycle. So you've got the spectrum here from big, womb to tomb of a product, and then the depth from the system all the way down through the material. So just for my own putting these into different common terms, I just started calling it the vertical thread, a horizontal thread, which is the life cycle view. This is the system of systems all the way through the material view. But all of that just enables you to understand the product. To connect it to a physical element, you're going to need some kind of lateral thread, and there's probably better terms out there, but allows you to connect the virtual to the physical. The lateral, because without connecting, go back to the why, if I can't make predictions of a physical product before it happens, I'm kind of missing the whole point. That's enabling the customers to make informed decisions. So you got to have some connection between the physical to the virtual and updated continually. So you end up with a depth across here and a breadth across the entire life cycle. These are an example of the ecosystem collaboration that makes up that entire spectrum. And you start down here with some theoretical science, down in this area here where you start looking at the types of professional organizations that are involved in this. From a professional organization standpoint only, you got a lot of commercial bodies and academic bodies that are involved in this as well. I just took this from a professional society standpoint of where does AIAA fit into here and where does it need to work? And then applied science. As you kind of move up this spectrum here, you get into more applied science in this realm here. You get into legislative action up here that makes it a reality of where can we put this into use? Why are we doing it? So there's a large progression of maturity of scientific foundations from this bottom portion all the way up through to you actually get something into production. So that's another way of looking at this ecosystem. This is dealing with the complexity involved in it. And Dr. Raz will be able to share a lot more about this because he's familiar with the complex systems working group. The important part to come out of this, if you don't know anything about Kinefin, just go get this source here. It explains a lot about what we're talking about when you start looking at different groups of people. Everything you're learning in school is primarily over here in the known and knowable domains. Either I know it and I can go build it, or I can know it and figure it out. So a lot of the fellows in our organization reside up in here in the knowable domain. What I'll briefly mention is the complex domain over here because it gets really important to understand that's how the different professional societies can work together. That's how a lot of the different supply chain elements can work together. This is how we can understand the value associated with it is this complex sphere. So in complex systems engineering, you end up with a new way of looking at it. You got collaborative engineering that goes the depth here from system through subsystem all the way down to material. Got concurrent engineering that's going womb to tomb on the life cycle, concept development, production, route to retirement. Those are, I'm just calling traditional systems engineering. And it includes the known and knowable domain that's shared underneath these spheres of influence. Under complex systems engineering, though, you've got these new areas that you got to focus on: complex, chaos, and disorder. They're all described in that Kinefin paper. And I'll just focus a little bit on the complex side because that is of where emergent behavior usually occurs, because now you're accounting for humans in this area. Emergent behavior does occur in these physical other elements. There's emergent behavior between a system and a subsystem. A subsystem only has emergent behavior because of behavior that each unit doesn't have, but together collectively a subsystem does. The important part is the emergent behavior is not as prevalent and as unanticipated as it does with humans. Humans are a finicky bunch, and they have different ways of influencing everything on this page. So my point to this is complex systems engineering has to be extended through model-based systems engineering. It can be done through traditional systems engineering, but it's very painful and very expensive. So why would you even want to go do it? You have to do it through model-based systems engineering, and then you can extend out into complex systems engineering. Model-based systems engineering includes pattern-based systems engineering, and that's where you can make a lot of ground fast and get that speed that will enable the DoD to see the benefits that they're wanting to get. You've got to get past model-based and get into pattern-based systems engineering. What's coming next after pattern-based systems engineering? Intelligence-based systems engineering. That's what's going to be extended out of pattern-based systems engineering. So just a precursor of what's coming next. There's a lot of good work inside the NCOSE pattern-based working group to explain this. But the important part to take away from this is pattern-based systems engineering gives you the speed, but it's enabled through model-based systems engineering to account for the complex systems engineering elements. Complex systems engineering allows you to do what is called paradoxical mindset inside the CERC reports, where you can look at the entire landscape and see the big picture and then zoom in on excruciating detail and then go back to the landscape. So you go back and forth, and you got to do that constantly to understand the implications of how this detailed view will be changing based on the big picture, and how the big picture is going to be changed based on this detailed view. So this back and forth occurs, and that's what systems engineers are really good at doing, and better than other disciplines, is going back and forth on those views. So just keep that in mind. You have to keep that paradoxical mindset in place. One of the ways, the best way I've just heard described to look at how do you do that across an entire life cycle is this Agile systems engineering lifecycle management pattern. There's some links here that will describe this in excruciating detail. The important part of this is to recognize the life cycle all the way from the beginning to the end and how different people view it. So you're going to have this target system here that you want to go develop, and there's deep knowledge inside this target system. And then you're going to have this second system here that's going to look at all the processes necessary to learn and to execute everything that's necessary to make a better target system. So there's learning going on here. There's updating of how you do learning better. Then you have this third system out here that's looking at how do you make a better targets. This number 2 system has nothing to do with the target system. It's how do you make a better environment here for learning? How do you make a better process for executing any kind of target system? So a lot of the academic stuff is out here in the system 3 world. Standards are out here in the system 3 world. And so you get this progression down here to the target system that has to be in place. Once you have this information lined up in place, there's a lot of depth inside every one of these blocks. That's your digital thread. You end up with a digital thread lining all these different disciplines together because it's information flowing across these different blocks to realize a target system. So all of that to get into the digital twin. The digital twin, we just put out a position paper from AIAA and AIA on what is a digital twin and what's its value. See the long definition up here of what that twin is. We didn't like that definition. It just turned people off. So we came up with a short definition that basically said, well, you can read it. The important part out of this short definition is a connected physical asset. Has to be connected. If it's not connected, you don't have a twin. Has to be physical. If you don't have a physical asset, you don't have a twin. And it's an asset. It's not a physical system. It can be an asset, which can be a system. It can be a person. It can even be a behavior. It's a physical asset that allows a digital twin to exist. So we came up with a real short definition and go through the paper to explain it. Why we looked at working with AIA versus just going at it with AIAA is because there's a natural synergy between the different organizations. AIAA has a very strong technical focus. We got that depth in from system of systems all the way down to material level. AIA brings together the business benefit. Why are we doing this? Why do we even care about knowing anything about what that better way of doing it is? There has to be a business benefit. So they have the more horizontal view across all of the business areas and understanding what's the business focus. So we teamed together and produced a digital position paper. That digital position paper is out just this week. In fact, it got published and it's out on AIAA's website, AIA's website. There's the links there. You'll have these slides so you can get them afterwards. And this digital twin position paper, it's a position paper. It's a guide. It's not going to go into excruciating detail about how any target system can create a digital twin, but it does give some definition of what is it, why are we doing this, and how could we do this together. So this is the summary of that position paper, where the definition of it, it's a connected physical asset that covers the entire product life cycle. And why are we doing this? It's shifting the right-hand side of the curve to the left-hand side, basically is what it's doing to be able to reduce late life cycle defects. If you want to put it in a nutshell, that's what you're doing here. And that by reducing late life cycle defects, hopefully eliminating them, that adds to significant decreases in resources and costs. And resources can be people, can be money, can be anything to keep aerospace assets operational. So that's kind of the summary of the position paper. This is a graphic that helps illustrate what we're talking about with a connected physical asset. There's the physical asset down here, and it's connected to a virtual asset by serial number or by tail number or by whatever number you want to put on it. For engine companies, they do it by serial number of each engine. For aircraft, they do it by tail number. You know, you start breaking these down and you get different digital twins of each element inside these things. And then you can even get aggregate digital twins and start looking at fleets of aircraft and predicting what happens with the fleet. There's a great example of digital twin that Georgia Tech has done of their entire campus. every building on Georgia Tech campus has a digital twin associated with it. And now they're able to predict surges of energy consumption and how to mitigate that and what can be done to reduce their electricity bills, for instance, or gas utilization or whatever. So don't think just physical asset as aerospace on this. There's a whole nother world to this inside like Georgia Tech's digital campus. It does align to DoD's strategy on digital engineering. If you've not read the DoD digital engineering strategy paper, I highly encourage you to do so. It's a short read, they're about 35 pages long, and it's very well written. That describes these 5 tenets over here. These are the 5 tenets of their digital strategy, of what they're trying to do. And I'll let you read those on your own. Over here, we have the digital twin tenets to help shape those digital engineering tenets. So they're aligned. We're not going off and creating something that is not aligned back to strategy. Go on. So these are my last couple of slides. I have next steps that we're doing within the Digital Engineering Integration Committee. We are collaborating with a bunch of organizations. There's a lot of them for creating a position paper on the digital thread. That's actively what we're doing this year. We did the digital twin position paper last year, just got published this week. We're doing digital thread this year. And then we're looking at doing digital ecosystem and digital system model last. Like I said, this one's less mature in people's minds about what that actually means. It involves a lot of different disciplines and how do they work together. It's really fun. Then we end up with consistency management. If I go back to the Agile Systems Engineering Lifecycle Management pattern I mentioned on a couple of slides, there is consistency that has to be implemented between every one of those lifecycle blocks. That's both internal between the thread, the twin, the ecosystem, and the digital system model, but also externally between how the different elements that I've shown on that Venn diagram relate to each other. So you get model-based X and trusted repositories. What does it mean for a trusted repository? That is a subject that is really ripe for exploration and is being explored. High performance computing. There's a difference between high performance computing and doing a lot of batch files that take a week to run, and yet doing cloud computing where I can get a lot of people on a collaborative network. Those are going 2 different paths. Digital engineering, making it tangible. We're going to build out position papers and then start doing implementation plans to make the position papers real. So this is, I think, my last slide before I get off the stage, where we're implementing digital twin position paper recommendations. I talked about the vertically structured tier, the horizontal interface. It's about as big a scope as you can possibly imagine. And drafting the digital thread position paper, and then the consistency manager role to make sure things are consistent, not vertically, but also horizontally. And it gets into semantic checking. And that gets into a lot of areas of recent investigation within systems engineering that starts using graph theory for looking at model-based systems engineering SysML models just by themselves. So an example was done where they looked at Sandy Friedenthal's spacecraft model on the internet and did a quick consistency check on it, and it's not very consistent. And It's because the amount of requirements, what's important came out of it. And, you know, that's one that's been touted as really good, and it is really good. But we got to get deeper into our system models to understand how you're going to check it for consistency. And then lastly, uncertainty quantification. There'll come a time in the future when we're not looking at preliminary design reviews or critical design reviews, but now we're going to view them in terms of uncertainty quantification and how how much risk was reduced, quantified how much risk was reduced, and when are you ready to go build it versus how much risk remains. And I'm not talking qualitative, it's going to be numbers associated with it all. So that was my presentation. Got about 5 minutes for any questions. It's a whirlwind. I apologize for that. There's a lot of more depth underneath every one of these slides that we could go into a separate workshop on, and there has been workshops on. So this is meant as a skim the surface and allow you to know kind of around the world what there is, but it's not going to go into depth unless we get together for a good couple of hours. Thanks, Ollie.
All right, thank you very much, Matt, for a wonderful discussion on digital engineering. I know this is a very hot and emerging topic in DoD and other disciplines as well. So I'd like to open up the floor for questions. Please, if there are any questions for Matt, please fire it away.
Hello.
Hello. Yes, hi.
It's Edward, Edward Huang. I'm associate professor at the SCUR department. And first of all, I would say thank you for that wonderful presentation. I have a one, let's say, comment on this. Let's say, my work is on the MBSE. So I know right now, let's say MBSE play a very, important role for this digital engineering thing. Let's say right now, as I know, let's say SysML 1.6 or 1.7, there is a one major issue. Let's say when we want to do all these kind of, let's say, digital engineering, all these SysML model may not be the best way because they lack a certain, let's say, capability to do this kind of integration. So that's the reason, let's say right now, or I'm in the like the 2.0, let's say committee. What we want to do is we want to make sure all these SysML model, they will become like a public, let's say, something like a controller, so that everything in the future, if you want to do the digital twin, then let's say SysML model and all your evaluation or simulation model, this the kind of thing, they can like extremely do the integration. So I think that we can see like next year or 2 years, there will be a big change from the SysML side. So that's just the comment I want to make.
I appreciate the comment. I've heard similar comments from a lot of other industry partners about SysML 2.0 and how they're trying to shape it for expanding SysML models beyond the limitations that we have right today. So I appreciate the input. Thank you for that. I welcome Dr. Roz or Dr. Huang, your help on putting those comments and sharing that within the Digital Engineering Integration Committee. We have a lot of industry fellows on the digital system model group that are taking a industry's perspective of how they can use the models. I don't know if we have as much representation from a SysML 2.0 viewpoint, and that would be really helpful to have that you could bring into this. So I welcome your input. That would be very helpful. Thank you.
I know, Matt, time is of essence. If that's okay with you, maybe we can continue the Q&A for a couple more minutes. But I do want to, all the participants, if you want to, leave, that's okay too.
Yeah, I'm good for about 5 or 10 more minutes. Sure.
Okay, that sounds very good.
And if anybody has any questions that maybe they've realized after the fact, my email is there on the cover page. Feel free to reach out to me and fire away with questions. And I may not know them. I but I know a lot of people that probably do know a lot more. If you start getting into Kinefin, I'm probably going to refer you to Dr. Ross. He's the one that would know a lot more about where to go with that, or refer you to Dr. McEver out of Johns Hopkins. He knows a lot more about that one as well. So I can at least point you in the right direction if I can't answer it myself.
Ali, there's a question in the chat message.
Sure, Bas, I saw that. So there's a question from the chat is, the virtual twins of subsystems are developed based on some mathematical formalism. And now these formalisms are specific to the class of systems they can model. For example, time-driven versus event-driven. So any theoretical attempt to develop some unified mathematical formalisms to combine those? So Bas, if you would like to elaborate more on this question, please feel free to do so.
Where does the chat, so I can see it?
Okay, the question is about combining theoretical formalisms to have a aggregate virtual twin that is based on some robust mathematical formalism.
It's a ripe discussion on what does the twin need to do, and that's where I go back to the why, because what does it need to do? It needs to enhance decisions by the customer. And if I can allow the customer to make better decisions about predicted future experiences that the physical asset's going to undergo, then have success. So does a digital twin need to be an aggregate of every single model of that exists of that physical asset? It probably is going to be a series of models that it's like I didn't like the authoritative source of truth. I like the authoritative source of knowledge, and it's authoritative sources, plural for me, because it's not one source. It's going to be many different sources that combine to provide answers for that physical asset. So the digital twin right now is kind of a concept, and what does that entail depends on the value associated with the person using it. So if it is for a business perspective, you probably have a different set of models than other ones that would also represent that physical asset. So how do they aggregate and combine is a lot of discussion right now.
Right. Yeah. It's Edward again, and I also have some point to add on to this. As I know, let's say several companies, they do something we call best like white box approach and also black box approach. Depends on the what kind of digital engineering they want to implement. So in this case, if they choose the, let's say the black box approach, they only describe, I would say, the meta description of that model. So we may not even know the model is in detail. So that all these kind of, let's say, system model, they only talk about, oh, I will have several analysis model, some analysis model, some simulation model. Here is there, maybe just input, output, that's it. And then some digital twin, they would describe in like the white box approach. They may even say, oh, here is the theory I'm using. Here is something I will put everything in my knowledge repository. So it still depends on the approach they are taking. But I think this is an open question for sure. So
it certainly is, and we need help putting together useful ways of combining them. Everybody has their own. Here at Northrop Grumman, we have a lot of very elaborate ways we're combining models, making an aggregate digital twin. And other companies, they have their own as well. How do those two work together is where we end up with those differing viewpoints of different charts, because you're approaching it with different values and different methods. So there has to be some way that we may not reach the exact same, but at least we can get what we call a harmonization of data, so that we're at least talking apples and apples here instead of completely different. Now, whether or not it's proprietary and it's a black box view, absolutely. It gets into a lot of proprietary data that people just don't want to let out. That's one of the reasons out of the Digital Engineering Integration Committee, we want to have implementation plans that are non-proprietary, that are out in public view, so that we can try and address these issues of how can different organizations do this without a lot of NDA, non-disclosure agreements, NDAs, in place between a supply chain or contractual obligations in place. You know, this should be a way that we could universally discuss how we could put these together. And that's what we're going to be working on. That's the next step.
But thank you, Dr. French. Thank you very much.
Thank you. I appreciate everybody's comments. You have my email there, and I'll send these slides through to Dr. Roz, so that I don't know if there's like a central repository there at George Mason. You can share these, or just email them out to the different participants on the call. That'd be fine too.
I think Matt, that would be great. So any other questions? I know we're getting a little over our time limit here. We still have 3 more minutes before your 10 minutes timer expires. So any questions from the audience? One question I had for you, Matt, is how about keeping the digital and the physical system in sync? What are some of the considerations there? I mean, for digital development or physical development, I mean, when you would expect that at some point they would get out of sync. So
yeah, there's a huge configuration management it gets turned on its head, where it's no longer just configuration management of a CAD drawing to a physical asset, but now models to digital twins, and the aggregate of those digital models to a twin. It gets huge. So in my opinion, configuration management gets elevated all the way up to a position that is about equal to the business case. It becomes as important as the costs of what the endeavor is going to be. It becomes as important as the performance of the model itself, because without that, you lose that chain. And so there is a huge issue with configuration management that needs to be completely fixed. But yeah, they're keeping them synced. DoD world, that's my world. That's the one I live in most of the time. I don't do a lot in the civil world. It's an issue because a lot of the DoD missions, we don't have the data. We don't have the information from the missions that they've run. So the digital twin and the physical asset are not in sync, because the physical asset's returned without any knowledge of what did it happen, what happened to it. It went through several experiences that we have no insight on. So how do you update that back to the digital twin so that now they're back in sync and you can make accurate predictions? It gets into the data and the information flow. So yeah, that's the digital thread of how you can get information flowing between different elements.
all right, nothing. Thank you for that response. And any other questions? I think we're right at 12:10, so I want to be very respectful of your time. And I do want to thank you very much for sharing, these insights on digital engineering with the SUR department here. So appreciate it.
And I'm open to, and just a last call. I don't claim to have the answers at all. I'm just sharing what we've done and where we're at, and welcome help in defining what the answers could be and working with other industry players on this stage. So, feel free to reach out and hope to work with all of you, especially being my alma mater. I have a special place in my heart for George Mason and want to continue this relationship. So I appreciate it. Thank you, Ali, for putting this together. I appreciate everybody joining and at least entertaining me for an hour of your time as we went through kind of this journey that we've been on within AIAA and what all the factors are that came together to enable it.
All right, no, it was a pleasure to have you, Matt, here as well. So thank you, everyone, for joining. And if you have any questions for Matt, you can reach out directly. And if you need the slides, please let me know. I'll get the slides from Matt, and I'll be happy to distribute as needed. All right. So with that, thank you, everyone, and have a wonderful weekend. Thank you, Matt.
Thank you. You have a great weekend.